till now we have done logical and logical or, okay. These things we have done, logical and logical or. So, this logical and actually it is set theoretic and was for intersection, set theoretic intersection, or we also defined it like this, minimum operator. Okay. Similarly, logical or actually it is set theoretic union, or it was maximum operator, max operator. This we have done. Okay. Now, whatever we have covered in fuzzy set, there for these fuzzy sets we had the membership function as crisp, that we considered. Any fuzzy set we had several examples we have discussed, and there for all the examples we took the membership function as crisp 0.1, 0.2, 0.5 or 1, but in between 0 and 1, in 0 and 1. But again there is a question that human being or this membership function may not be fixed, because while we are doing the examples I told it is user oriented. I can give 0.5 for some value, you can give 0.6, somebody can give 0.4, like that. That means for the human beings this membership function may not be fixed. Okay. So, that may be again fuzzy, actually that again should be fuzzy. So, again Professor Jade, father of fuzzy, he gave the notion of fuzzy sets where the membership function itself is fuzzy. Okay. Membership function itself is a fuzzy. So, from there we will go to the different types of fuzzy sets. Okay. So, whatever ordinary fuzzy sets we have done, suppose that we call as type 1 fuzzy set. Okay. That means we do have then type 2, type 3, etc. Okay. So, let us define then what is type 2 fuzzy set, okay, and consider that whatever we have done fuzzy sets, those are type 1, name is type 1. So, let us see how we define. So, let us define type 2 fuzzy set. So, this is a fuzzy set, it is a fuzzy set which has the membership function as type 1 fuzzy set on 0 1. Okay. What is type 2 fuzzy set? Type 2 fuzzy set is a fuzzy set whose membership function itself is of type 1 fuzzy set. For understanding, we have fuzzy set such that its membership function itself a fuzzy set. So, we have given the name type 2 whose membership function is type 1. Similarly, I can increase all those means generalize to other type 3, type 4 fuzzy sets, but if you remember that operators that we have defined, okay, those minimum operator or union, intersection, okay, complement, all those operators again it cannot be followed by the earlier definitions. So, we do have then the different definitions, but for that we need an important principle, that is your extension principle. So, that we will study little bit afterwards. Okay. So, we have to use this extension principle to define all those operators that we have done, at least those 3, union, intersection and complement. Those are the most important operators in fuzzy set, because from there we are deriving all those things. Okay. So, let us now define type M fuzzy set. So, type M fuzzy set will be, it is a fuzzy set which has the membership function as type M minus 1, and remember M should be greater than 1. Okay. So, a fuzzy set is type M fuzzy set whose membership function is of type m minus 1. This is just generalization, but if you see up to m equal to 2 I can see, okay, but after m means it is difficult to visualize, means after 3 means if m greater than equal to 3, then it is difficult to visualize as your n dimension space. What is 5 dimension, 6 dimension? Only visualize means we think okay it is there, n dimension, okay. Like that it is difficult to, but for generalization I can write type 2, 3, 4 up to type m. M is greater than 1, okay. Now we can have other fuzzy sets whose membership function may be random variable. So that is actually a amalgamation, membership function may be random variable, okay. Fuzzy set whose first element is your element x1, x2, x3 and maybe its membership function is random variable. That is the combination of fuzzy theory and probability theory, okay. So those things we do not have, but you should know that membership function means you should think like that, means membership function may be random variable. So you can combine that, those are hot topics actually, people are doing research on those which are not in your course now, but you should know all those things, okay, at least the idea. So with this we will now generalize the fuzzy sets, an important fuzzy set that is called generalization of fuzzy set, and we have in this that is called Intuitionistic fuzzy set. Intuitionistic fuzzy set, okay. A fuzzy set is called an Intuitionistic fuzzy set, okay, where we have ordered triplets. In fuzzy set we are having ordered pairs x, mu a bar x. X is the element, mu a bar x is the membership function of x for that a bar fuzzy set. Here it is a ordered triplet, okay. Intuitionistic fuzzy set is a fuzzy set defined by ordered, and suppose we have this as the Intuitionistic fuzzy set, we define as x mu a bar x. Up to this you know, if you a bar is a fuzzy set, then we will have x and mu a bar x, okay, where mu a bar x is the membership function of x, that you know. Now only one more notation will be added there, that is mu a bar x, such that x belongs to x. So this is an ordered triplet. Mu a bar x again is a membership function from capital X to 0 1 into 0 1. This is also a function from capital X to 0 1. Mu a bar x is a function from x to 0 1 and mu a bar x is also a function from x to 0 1, but this actually is the membership degree of x, okay, means or degree of membership of x, and this is actually degree of non-membership, degree of non-membership, degree of non-membership. So we can visualize this very easily for your ordinary fuzzy set, for your ordinary fuzzy set. Ordinary fuzzy set, if I write for ordinary fuzzy set, we can write this mu a bar x is equal to 1 minus mu a bar x, because complement, and I can write it in the form. Here one more condition is there, that is this addition of this mu a bar x plus mu a bar x should be between 0 and 1, okay. It cannot exceed 1, okay, cannot less than 0, okay. This is the condition for these two. That is why if I write ordinary fuzzy set as like this, a bar is equal to x mu a bar x and 1 minus mu a bar x, which is your mu a bar x, such that x belongs to x. So now this is satisfying. Okay. So, for this case we can write. Okay. So, this is another definition of generalization of the fuzzy set, that is called intuitionistic fuzzy set. Okay. Again, there are many things in intuitionistic fuzzy set. Again, those we cannot cover, but just I am giving the idea of different fuzzy sets. Okay. Okay. Type 1, ordinary means type 1, fuzzy set of type 1. Okay. Type 2 operators we will do afterwards. Okay. 2, 3 operators we will do. Now, averaging operator. See, this averaging operator is what? Means average of the fuzzy sets. Average of the fuzzy sets. If I have two fuzzy sets, suppose A bar and B bar, this is actually first aggregation, fuzzy aggregation. Means suppose A bar is something, temperature, B bar is wind. Okay, you want to aggregate, because but you do not have the data like digital data. Okay, you have A bar as fuzzy set given, B bar is something fuzzy set is given. Now, you want to aggregate that and you want to conclude something using your temperature and wind. Understood? So, how to do that? This is, there are two averaging operators actually here, that is called fuzzy AND operator and fuzzy OR. These are two averaging operators. So, these are defined as this, for this fuzzy AND means the membership function mu and of, suppose these two fuzzy sets membership function, that means mu A bar x, mu B bar x is defined as gamma, some constant, minimum of mu A bar x, mu B bar x plus 1 minus gamma into mu A bar x plus mu B bar x divided by 2, where this gamma belongs to 0, 1, okay, and x belongs to x. Okay. This is your fuzzy AND operator defined as the membership function defined for these two fuzzy sets, membership function mu A bar x, mu B bar x as this. Now, you see gamma belongs to 0, 1. Okay. If I put gamma is equal to 1, gamma is equal to 1, so this term is 0. So, you will get only this term. That means, this fuzzy AND operator becomes a minimum operator for this gamma is equal to 1. If I put gamma is equal to 0, gamma is equal to 0, this term will not be there, okay, only you will get this term. And what is this? Arithmetic mean. Arithmetic mean between these two membership functions, gamma A bar x and gamma B bar x. So, that is why it is called averaging. The name comes from there, averaging. Okay. For gamma is equal to 0, it gives the arithmetic mean, and gamma is equal to 1, it gives what? AND or minimum operator. Okay. Similarly, I can have mu or, only the change will be here, max. Okay. So, we can write mu or mu A bar x, mu B bar x is equal to gamma max mu A bar x, mu B bar x plus 1 minus gamma mu A bar x plus mu B bar x by 2, and again gamma belongs to 0, 1, or I can write here gamma belongs to 0, 1. Okay. So, if gamma is 1, in both the cases we will get either minimum operator or maximum operator. So, it is minimum or max operator, and if gamma is 0, so we will get arithmetic mean. Okay? Very simple. So, this way we average. So, we have different type of another operator for averaging, that is called OWA, ordered weightage averaging operator. So, that we will define next. So, okay, we can erase. I will write. This is called OWA, or this is called ordered weighted averaging for OWA and operator. Ordered weighted averaging operator, OWA. Okay. So, here actually there we give for 2 fuzzy sets. Here I can have number of fuzzy sets. Okay. So, see here it is defined as, this operator is defined as mu of OWA x, x is an element. Okay. Suppose I have a number of fuzzy sets. Okay. So, if number of fuzzy sets, suppose r or n whatever. So, I will have this as summation Wj mu j x, where this Wj is your weighted values. Values means, so if I write W is equal to, so maybe this Wn, this is a vector of weights, where these are having condition that this Wi or Wj belongs to 0, 1, and summation this Wj is 1. These are the two conditions, means your weighted values are between 0 and 1 in the closed set 0, 1, and summation of this all W's are 1. Okay. So, now what is mu j? Mu j x is the jth in the membership. No, it is the mu means always membership. It is the largest jth membership of x. Okay. Largest jth membership value of x in A bar, or not, sorry, in all the fuzzy sets, in all means I will take one example, then it will be clear. Suppose I have been given 20 fuzzy sets, A1 bar, A2 bar, A20 bar. Okay. So, for that you have the W values, W1, W2, W20, no problem. Mu jx, mu x also it will be given. Now, you take the largest one, that should be first, means decreasing order you have to do and multiply and add. Okay. Let us take that example for those who have not understood. Suppose I have 10 fuzzy sets, and whose membership function are mu1 x to mu 10 x. Okay. We have, these are 10 fuzzy sets, and I have been given W values as 0.3, 0.2, 0.15, 0.12, 0.07, 0.05, 0.04, 0.03, 0.02, 0.02. So, see all these entries in this W are between 0 1. Okay? And if you add all these, it is 1. If it is not, we have to change somewhere. Okay? So, I hope this is summation of these Wj's are 1, and we have been given the membership of this fuzzy sets for that x. I want to find at x, see mu OWA x. If we change x, all will be changed, okay, as per their membership values. Okay. So, u are given, u values are given as 0.2, 0.3, 0.5, 0.8, 1, 0.6, 0.5, 0.4, 0.3, 0.2. Now I have to have this mu j is equal to, suppose u dash I am writing. So I have to take the highest one, largest one. So largest one is 1, then it is 0.8, I think 0.8, yes. So like that you just arrange this, okay. Then you multiply this into this plus this into this, like that you will get mu OWA, understood. So our mu OWA x will be first 0.3 into 1 plus 0.2 into 0.8 plus other values. So whatever you get after this solving, okay. So it is very easy to find. Suppose I have different fuzzy sets given. So weight you can define, or it will be given as per your application problem, and then membership values you can define, you know how to define depending upon your own experience, or it should be given by the engineers or whatever who is given you to model. So you do that, multiply that, you will get the mu OWA, okay. Okay. So it was your ordered weighted averaging operator. Now the most important thing, that is the extension principle. This is very important. The extension principle. So we have the universal set X, which is actually product set of different universal sets x1 cross suppose xr, okay, product sets x1, x2, xr, and we have fuzzy sets in these as a1 bar, a2 bar up to ar bar, okay, a1 bar, a2 bar up to ar bar, okay. So suppose, although it is, I suppose that this is your x, okay, and here you have the fuzzy sets as a1 bar, ar bar, okay. So any element x here will be actually, suppose x1 contains in a1 bar, x2 in a2 bar, like that. So x I can write as x1, x2, xr, okay. That means this vector x1, x2, xr will be in capital X, okay. This is given, suppose. Now I will define a function, a mapping f from this x, okay, to another universal set y, okay. I will define a function f from x to y, okay, x to y, and what is that function? I define like this: y is equal to f of x1, x2, xr, okay. So here it is your y, and y is your f of x1 to xr, okay, okay. Now if we define this, then this extension principle defines or introduces a fuzzy set here B bar, okay. Then the extension principle gives a fuzzy set, or defines is better, defines, then the extension principle defines a fuzzy set B bar in Y as how, okay, understood. This is your fuzzy sets A1, A2, AR are there. We define a function y equal to fx, f we can define anything, x square means x1, x2, xr, suppose summation is square, like that, any function. So if you define that, then B bar will get a fuzzy set as B bar or okay, as y and mu B bar y. See, that will be a fuzzy set, so elements will be y, but remember y is actually f of x, okay, f of x1, x2, xr, and mu b bar y such that y is equal to f of x1 to xr, and x1 to xr belongs to capital X, and x is x1 cross x2 cross xr. Okay? So, this, but main problem is that with this, what is that? Okay? This membership function, what is that? So, where mu b bar y is sup of minimum of, okay, sup minimum of mu a1 bar x1, mu a2 bar x2, mu ar bar xr, if f inverse y is not equal to null set and is equal to 0 otherwise, and this sup, for this we have this f inverse y, here this x1 xr should belongs to f inverse y. Okay, see the definition. See the definition. We have the fuzzy set as y mu b bar y. Okay. Now, this mu b bar y defined as supremum or and then minimum. First you take minimum of those, mu a1 bar x1, mu a bar x2, mu a bar xr, take the minimum and then take supremum of that. But for those which are belongs to f, we will take example, it will be clear, very clear. Okay. So, f inverse y, okay, if f inverse y is not equal to phi and this is 0 otherwise. So, let us see for r equal to 1, then it will be more clear. R equal to 1, r equal to 1 means whatever we have done ordinary fuzzy set. Okay.
Why did we define the mapping?
See, why did you define?
Mapping. What is the
No, suppose I have some fuzzy set.
use of this mapping?
I have some fuzzy set. I want, suppose I can take, suppose r equal to 1 first I have to do, that is why I told r equal to 1. I have some fuzzy set here. I define, suppose y is equal to x square. Then what fuzzy set you will get mathematically? It is not easy that you will just square those membership value and you will get the fuzzy set. You are understanding? What is the intuition? Intuition is if y equal to x square, whatever x values are there, you just means square those and you, but you will not get. So, this is the definition that whatever function you will use, I will sign function. Function of a fuzzy set. How we get that fuzzy set? By using any function that you will define. Okay? So, let us take for r equal to 1, I will erase up to here. Let us take r equal to 1 and see what is if r is equal to 1. See, if r equal to 1, so we will get b bar as y mu b bar y, because I have only fuzzy set a bar. R equal to 1 means I have only single fuzzy set a bar or not. So, then y is equal to only f of x. We have only x, okay, and x belongs to your capital X, where a is in x, a bar sorry, a bar is in x actually, okay, b bar is your in y. Understood? So, now this mu bar y, mu b bar y will be what? In this case only 1 is there, so only supremum, okay, supremum of this mu a bar x only, okay. If f inverse y is not equal to phi and this sup on x belongs to f inverse y and is equal to 0 otherwise. Now, I will take two examples, one for r equal to 1 and another for r equal to 2, then it will be clear, I think. Okay? Let us take first example let A bar is a fuzzy set given as -1, 0.5, 0, 0.8, 1, 1, 2.4, and it is given that Fx is your x square. Okay? I want to find B bar. What is B bar? B bar is what? Okay? I have been given a fuzzy set A bar where these are the elements ordered pairs and given the function is x square. See how we are getting B bar. Okay? Now for the elements these x, if I am using Fx equal to x square, these are square. So if I say this is your A bar, this is your B bar suppose. So if I say this is your 0, this is your 0, so 0 will be mapped to 0. Okay? Okay? I am not writing every membership function, only the elements. Okay? 0 will be 0. Now if this is 1, 2, okay, this is 1, 2, 3, 4, this is -1, so maybe it is 1, -1, 2, 1, 2, 3, 4. Now -1 will map to 1. Okay? So -1 is mapping to 1. Okay? 1 will map to also 1, 1 square, 1, 2 will map to 4. Okay? So what are the elements in B bar then we are getting? 0, 1 and 4. But what are the membership functions? That will be given by extension principle. So that we will see what are those. So elements in B bar, so I have 0 and mu A bar, sorry, mu B bar 0. I have to find those mu B bar 0, 1, mu B bar 1 and lastly 4 mu B bar 4. Is it okay? Now I have to find this membership function for 0, 1 and 4. So it is very easy. Mu B bar 0. Okay, how will you find? It is soup of the only soup. Soup. So soup of see 0. So first it is belongs to F inverse 0 and only 0 belong here. Okay. Now 0, what was that membership function? 0.8, only 1. Only 1. Understanding?
So 0.8.
So I can write it 0.8 and this is your 0.8. Okay. Now come to 1, then it will be more clear. So mu B bar 1 is equal to soup. Now you see your F inverse 1, F inverse 1 is two values, 1 and -1. Two members are there, but for 0 only one member was there. So yes, so it is 1 and -1, and then I have to take soup for 1, -1 is 0.5 and 1 is 1. Okay? So 0.5 and 1, so this is 1. Understood? So for this function, so similarly I can have mu B bar 4, this is soup of F inverse 4 and that is your 2, and soup of this is, what is 4? Sorry, 2, this is 0.4 and this is your 0.4. So you saw, it's okay. So now I can replace this mu B bar 0, mu B bar 1 and mu B bar 4 by first one it was 0.8, then 1 and 0.4. So I got the fuzzy set B bar as 0, 0.8, 1, 1 and 4, 0.4 I think. Okay? This is okay, very simple. So this way, given a function, okay, Fx, you can define a fuzzy set in y, okay, for r equal to 1. Okay. And you see for r equal to 1 we have only sup, that it is clear. When r is more than 1, then it will be sup of minimum, you will see in the next example. Okay. Suppose we come to the next example to see what is happening there. Should I erase? No problem. So, example 2, and that is suppose for r equal to. So, here r equal to 2 means 2 fuzzy sets should be there in X. R equal to 1 we are having only one fuzzy set A bar. So, here we will have A1 bar one fuzzy set and A2 bar another fuzzy set. Okay. So, A1 bar are given as suppose -1 1 0 0.4 1 0.2 2 0.5. So, this is your first fuzzy set A1 bar. Okay. A2 bar, this is your -1 0.5 0.08 1 1 2 0.4, and your F, because we have two A1 bar A2 bar, so we should have x1 x2. So, f of x1 x2 given as suppose say x1 square plus x2 square. This is your function. Now, I want to find b bar. Okay. Now, let us first write in symbolic form. Okay. So, what is your b bar? B bar will be your y mu b bar y, such that y is a function of x1 x2, correct, and your x1 x2 belongs to where? Capital X. Okay. Now, what is b bar y? It will be sup of minimum, and here sup will be on f inverse y, where only x1 and x2. In general, it was x1 x2 xr, if you remember. It is x1 x2 f inverse y. Okay. And minimum in all those mu1 bar x1, all those minimum first, that is why sup is there. You will see when you solve this. Mu a bar x1, mu a1 bar x1, mu a2 bar x2. Okay. If f inverse y is not equal to phi and is 0, here it is okay. I have to extend this 0 otherwise. Okay. Now, let us find what about that b bar. B bar is what? Okay. Okay. So, b bar elements. Elements will be what? You know, will be -1 -1 -1 0 -1 1 like that, then again 0 -1 0, these are the elements. Okay. So, you see, so what are the values actually you will get? See, f x1 x2 is x1 square plus x2 square. You are seeing. So, if I take -1 -1, it is your 2, -1 square plus -1 square, -1 0 1 0 0 0. That means we have values 0 1 2 all. So, let us start with 0. Okay. So, for 0, so that means I have to take f of 0 0 is your 0 plus 0, that is your 0. Okay. 0 is the element, but what is the membership degree there in b bar? So, I have to find mu b bar 0. So, mu b bar 0, it will be what? See, sup of f inverse 0, and this will belong to where? What are the elements will be there? Only 0 0, only 0 0, but because only 0 0 is possible na for 0. Okay. So, 0 0, sup of minimum of Now you see, soup of minimum of this, minimum of what? 0 and 0, 0 is in first set, 0 is in second set, fuzzy set, 0.4, here 0.08. So, minimum of 0.4 and 0.08, the minimum is 0.08, soup is again 0.08. Understanding? Okay? So, it will be more understood when we will take 1 or 2. Okay? So, this is your 0.08. Let us now see about the 1. 1 means 1, how you are getting? Minus 1, 0, 0 minus 1, any other possibility? 0, 1, yes, again 0, 1. So, 4 possibilities. 4 possibilities, let us do that, then it will be clear. Okay? So, we will have this, I am writing directly mu b bar 1. Okay, now mu b bar 1 is equal to soup of belongs to F inverse 1. Now, what you are telling? Minus 1, 0. So, minus 1, 0, this is the first one. Then 1 and 0, sorry, 1 and 0. I am taking first A, okay? 1 and 0. Next is 0 and minus 1. 0 and minus 1, and last one will be 0 and 1. 4. That is why minimum of all those you have to take and then soup. So, now you soup of, now you should have minimum of, see, minus 1 and 0, minus 1 membership value is 1, 0 is 0.08, I have to take minimum of that. I am writing 1, then others 0.08, I have to take minimum of that. Again 1, 0, 1, 0, minimum of 0.2 and 0.08. Okay? Then 0 minus 1, 0 minus 1. So, 0.08 and 1, 0.08 and 1. Last is minimum of 0 and 1, 0 and 1, 0.08 and 0.2, 0.08 and 0.2. Understood? So, now I can have this soup of, see, soup of minimum of 1 and 0.08, you know 0.08, it is 0.08, it is 0.08 or not? 0.08, all are 0.08 in this case by chance. Am I correct? Somewhere I did mistake or what? Second?
Minus 1, 0.
Minus
0 minus 1. For 0 minus 1 for third one.
0 minus 1. 0 is 0.4?
Minus 1 is 0.5.
Oh, okay.
There it is 0.4.
So, it is me that I am written wrongly, it is 0.4, no, 0.4 and 0.5, yes. So, at least you have understood, that is okay. This is also changed, I think. 0.4 and 1 is okay. Okay. So, now this will be 0.4 and 0.4. This okay? Okay. Actually is what? Whatever elements are there, corresponding membership values you see, take the minimum directly. I am writing to make you understand. Directly you write the minimum values and take the soup. What is the soup? 0 point or not? 0.4 maximum. You can write max min also. Okay. So, 0.4. So, you see, so if I write, so there are other values also. I am not doing that. That is your homework. Okay. So, you can have others, means suppose I take 2 square plus 2 square, it is 8. Okay. I can have this and this, 2 square plus 1 square, 5. So, those elements you can generate, and you generate all those membership functions, okay, and you write finally B bar as, suppose I write 0, 0.08, 1 comma 0.4, so you have whatever, okay, finish that, very simple. So, that this way if you have 3 fuzzy sets, you can very well write 4, 5 whatever. So, in general I have given the definition for general R, and this way you can have the function of that, using the function you can get the fuzzy set in the another domain. Okay? Okay. Thank you.